So our goal here is to determine hyperbolic geodesics. Okay, this is of course standard Riemannian geometry, but we won't do that. What we'll do is use a lot of symmetries. So our first set of hyperbolic geodesics are vertical lines. So here we are looking at the upper half plane, and let's take a vertical line. Okay, perhaps it will be in another color. Okay, let's take a pair of points on it, P and Q, and we claim that the shortest path between P and Q actually lies on the line which I haven't yet given a name. Let's call it gamma. Okay, so here's the proposition. The shortest path between P and Q, so PQ and gamma, lies in gamma. And the proof is actually very simple. And the proof is that if given any path, let me call this something alpha from P to Q, projecting onto the line, onto gamma, shortens it. Now shortens it, I mean in the weak sense, that is, if it was already on the line, it does not actually shorten it, strictly speaking, it keeps it the same length. Okay, so let's project it this way. What happens? Why? Well, there are 2 points to note. One is that Euclidean length decreases. This is the case for projections always. That is to say, if I'm looking at a tangent vector like this, it's become a tangent vector here, which has become shorter. Projection always decreases length. Okay. Strictly decreases unless it's already in the projected space, in which case it keeps the length the same. But hyperbolic length is not Euclidean length. However, remember that the hyperbolic length, okay, I've written it like this, it's 1 over y times dh, the Euclidean. What this notation means, I've sort of changed the notation, but the key point to note is that you have a scaling factor. So let me revert to better notation. The hyperbolic norm is 1 over y times the Euclidean norm. The scaling factor is unchanged. This is because we projected onto a vertical line, and so is unchanged. Well, this is because it's independent of x. Okay, so thus we have a bunch of geodesics. So thus vertical lines are geodesics. Okay, so we have identified a bunch of geodesics. This is our start of our quest. Vertical lines are geodesics. Okay, but note we use 2 points in the argument. One, projection decreases Euclidean length, and second, the manner in which we are projecting, each point is moved to another point at the same height. So the scaling factor is not changed. Okay, so if I look at a horizontal line instead, okay, which was like this, for example, or any other line with any slope, and took the same picture, that is to say I had a line like this joining it, and I projected it down. Okay, so here this is not true. Well, why not? What has happened in this case is, well, certainly the Euclidean length has decreased. It always decreases when we project. But on the other hand, the scaling factor has actually changed. That is, the point which was higher, it's come down, and this has actually increased 1 over y. and how these two interact with each other is complicated, and we won't try to understand this. Okay, instead we'll proceed by symmetries. But I made this argument to point out this works for vertical lines and not for general lines. In fact, vertical lines are the only geodesic lines, as we'll see. Okay, so now to move on to the symmetries. This is what we'll use, but in specifically we'll use symmetries and circles. Okay, so well, let's just look at this. Lines and circles in C are given by, as frequently happens in geometry, circles by themselves don't form a nice set. In some sense, they're an open set. You have to include lines in them. Lines are a form of degenerate circles. Now, lines and circles are all given by an equation of the following form: P times ZZ bar plus some Z times Z plus Z bar times Z bar plus Q equals 0, where P and Q are real and Z is a complex number. Okay. Now this quantity is a real quantity. Okay. So this is a real number, and this quantity is of course mod Z squared. In fact, this quantity is just maybe twice the real part of Z times Z. Okay. So this is a nice way of putting the equations. It's a simple exercise to see the usual way of writing the equations of circles. This will be convenient to us, okay, because from this it